Okay, this is an introduction to differential equations. A differential equation is amazingly an equation that involves derivatives. So differential equation, it contains derivatives. An important part of what we do is to solve these. So when we solve them, the solution is actually an equation. So there's two types of solutions as well. There's the general solution and there's the particular solution. So the general solution is an equation with a plus c on the end, and particular solution is just an equation. There's no c, no constant of integration. And yes, we're going to use integration. And over the course of the next few videos, we'll be solving differential equations in three different forms. And I'll just quickly outline all three forms in this video, but this video is basically going to focus on showing examples, fully worked examples for the first type. The first type is where we have dy dx equals f of x. Now you're already familiar with that, so type 1, you're familiar with it. So examples, not surprisingly, are things like dy dx equals something like this polynomial here, 3x squared plus 12x plus 98. That's an example of one. Or another one might be, we have dy dx plus 12x equals 0, something like that. Okay, they're both type 1, so it's in the form dy dx equals a function of x. Now there's a process called separation of variables, and that's where we get the differentials and split them apart. Okay, what we mean by separate the differentials, that and that would be split apart and end up on opposite sides of the equation. Now separation of variables is not particularly important. It's not mandatory for type 1, but when we get to type 2 and 3, I'll be showing you the separation of variables. So that'll be shown fully in another video, although I'll probably just pop an example of it in this one just to get you thinking about it. So the second type, which will be shown fully in the next video, is something of the form dy dx equals a function of y, so we might say g of y. And examples of that might be things like dy dx equals, say, negative 0.7y. You can see the y on the right hand side there. Or another example might be something like dy dx minus 4 root y equals 0. Okay, and the third and final type, dy dx equals f of x times g of y. So the form is a function of x times some function of y. Okay, so examples might be something like dy dx plus y equals 6x squared y as an example of that form. Now a few parameters and definitions to clarify here. We're going to be focusing on first order differential equations. So first order DEs, I might say. Okay, first order differential equations, but there are other ones. So all of the ones listed above are first order. So we basically have dy dx, and that's all we have. They're the only derivatives we have. Of course, y and x are not necessarily the variables we're using, but they're first order, meaning that we only go to the first derivative. Okay, so that's our focus. But of course, there are other ones that are higher order, second order, third order. they're very important, but they're beyond the scope of what we're studying. So there are some higher order ones. Now, if we have a look at an example of a second order one, which is down here, so that might be a harmonic type situation, or it might be a situation where we have basically a damped or an amplified function. That one might be for something like a bungee cord over time, and perhaps the graph of the motion might do something like that. Amplification works the opposite, sound amplification. So you can see that that's a second order because the highest order of derivative is 2. So it's got the second derivative present. So we'd call that one a second order. But again, that's beyond the scope, but it's nice to know about it. And even though it contains a first derivative in it, it is a second order because it's the highest. But again, we're just sticking with first order. Now, getting back quickly to the general and particular solutions, I'm going to show you now an example of each, and I'll show you this in regards to just type 1, so where dy dx is equal to a function of x. Here we have an example of a differential equation, a first order differential equation to solve. Dy dx plus 12x equals 0, and I mentioned that one before. So what we do is, not surprisingly, we isolate dy dx, so dy dx equals negative 12x. And yeah, you know what to do. You take the integral of 12x to undo the derivative, and you've seen that before. No biggie, and y equals negative 6x squared plus c. It's not, as I said, it's not important, but an alternative just to show you how separation of variables works. This will be more relevant for the other two types. After this line up here, the separation of variables method would be like this. We get the differentials and split them up. So we would write this side here like that, and that equals 1 dx. And then we integrate both sides. And we have that on the right hand side. Sorry, I was thinking of a different question. We split them up like that, I should say. And on the left we really have 1 dy, so if we integrate each side, like so, we have y equals negative 12 times x squared over 2, and there's a constant. There's constants on each side, left side and right side. We bundle them together as a generic constant, and that's negative 6x squared plus c as well. It's not hugely important to do it that way for type 1. You can stick to what you've known before, but for type 2 and 3, you will be using the separation of variables method. Okay, so that's a general solution because there's a plus c. Okay, there's a family of solutions. Let's look at one now for particular solution. So for this one here, we know it's going to be a particular solution because we're given some extra information. Now that is really important. Almost always when you're given the extra information, you use it, okay, for a particular solution, which helps us with things like problem solving. So if they give you extra information, it's very, very likely that you're going to need to use it. So what we do to solve this one, we do the rearrangement, isolate dy dx, and we get negative 1 over 4 minus 3x all squared. And one thing you can do is rewrite that in negative index form. Like so. So dy dx equals all that. and then we go ahead and integrate. So y will be the integral, or negative the integral of that. Okay, and in a case like this, we can use a u substitution. So let u equal 4 minus 3x du dx equals negative 3. So dx equals negative du over 3. Okay, so when we go to sub, we've got u to the negative 2, and dx is negative du over 3, so we can put a negative 1/3 out the front, which now makes that positive there, and we have our du. And we can add 1 to the power, divide by the new power, with 1/3 sitting out there, plus c. So we can tidy all that up. So we've got negative 1 over 3u plus c. Substitute back in terms of x. So we have negative 1 over 3. Now we said that was 4 minus 3x. That's substitution. Plus c. So we have negative 1 over 3 outside of 4 minus 3x plus c. Now, to get the c, we use that given bit of information. So that given bit of information was y of 1 equals 2. So that means when x equals 1, y equals 2. So remember, we've got our general solution now to turn into a particular solution. What we need to do is substitute y equals 1 and x equals 2 into that. So 1 equals negative 1 over 3 outside of 4 minus 3 by 1. Whoops, no. That's 2. Okay, so it's a 2 outside. 2 equals, I should say. Alright, I subbed the wrong variable in. There we go, but I found it pretty quick. So, there we go. Now to solve for c, we tidy all that up, and so we have 2 equals negative 1 over 12 minus 3 plus c. So we have 2 equals, oh, another mistake, we've got a 3 there, that should have been. 3 by 1 is 3. So try again, and c equals 2 1/3. So we can update that equation now. So y equals negative 1 over 3 outside of 4 minus 3x. Now I'm going to change the 2 1/3 to 7/3. Scrolling down. Just put our answer in a better form. So we need to find a common denominator. And 3 times 4 minus 3x will be that common denominator. And it's really just algebra from here. So we have negative 1 plus 28 minus 21x. So negative 1 plus 28 minus 21x. I know it's coming up, so I'm just going to leave the bottom factorized. Okay, so we have 27 minus 21x over 3. See, I know there's going to be a factor of 3 coming up. That's why I left the bottom factorized. So denominator stays factorized. And take your 3, you got your 9, you got 7x, you got the denominator through 4 minus 3x. and we haven't got far to go now before we can present our answer. Now we got 9 minus 7x over 4 minus 3x, and restriction on the domain, the denominator cannot equal 0. So that's the solution, the particular solution for the presented differential equation.